This is part 5 of a series of lectures about Newton's Principia explained. In part 4 I summarized what Newton actually did, and basically he did a geometric proof about a property of an ellipse, which as a corollary said that the inverse square law was true if planets went around the sun in an ellipse. The geometric property is this, that in this ellipse here, that L is a constant in the ellipse. It's the distance from S. If you make a perpendicular line from S up to the ellipse, it's called lattice rectum. L times QR over QT squared, in this case, equals 1.39, and that it always equals 2CP times GV, over GV times QV squared over QX squared. And P is a random point on the ellipse, and so is Q. RP is tangent to the ellipse, QX is parallel to that, and QV, V is continuation of QX. Those are the basic lines there. S is one of the foci of the ellipse. So to take you through this, you're going to have to know some properties of ellipses that were widely known, I guess, in Newton's time, and not so widely known today. They go back all the way to Apollonius. Apollonius's book on conics. So I'm going to take you through some of the basics of conics that you'll need to know to follow the proof. There's only about 5 theorems from conics that Newton uses, and the rest are all things just from basic geometry. One thing different about the way conics was done back in Apollonius times versus now is all conics had multiple what they call diameters. Now in a circle, you can imagine there's a lot of diameters in a circle, but when we talk about a parabola, most people, if they had to say what the diameter of a parabola is, they would say that it was the line, like the axis of symmetry. And if you have the axis of symmetry and you pick a point on the axis of symmetry called B, and then you make a line, sort of a horizontal line, you get this line BC. Now back then they would call AB the abscissa and BC the ordinate drawn to that abscissa. And nowadays we think of that as the x-coordinate and the y-coordinate of this point here. And we learn things like y equals some constant times x squared. And that's true. Here I have the x squared over y being a constant no matter where B is. But something different in the conics back then is that the parabola and all the conics didn't just have one diameter. Really, you could pick any point on the parabola and call that the diameter. But if you're going to call that the diameter, then the ordinates for these geometric properties to all hold, they are not going to be horizontal anymore. It's only horizontal when the what's called principal diameter is at the vertex. The ordinates now have to be parallel to the line that's tangent to the parabola at that point. So as long as I make my ordinates going, here's B, C again, as long as they're going parallel to the place, to the tangent, to the parallel to this tangent, those properties about like parabolas, for instance, still stay true. So as you see, as I move B up and down, the x squared over y is becoming a constant, but the x and y are not perpendicular anymore. And if I move A around, you can see how the ordinates change. Now this number is changing over here, but once I fix the A at this point and I move B up and down, that ratio does not change. Well, the same thing is going to be true for ellipses. Nowadays we tend to think of an ellipse as having sort of a major axis and a minor axis, but the fact is, you could, if P is a point on the ellipse and we draw a line through the center of the ellipse and then continue it to G, they would call that a diameter of the ellipse. And in this case, because the tangent to the ellipse at that point is basically a vertical line, the ordinates that they talk about in their properties they figured out are also vertical. However, any point can be, P can be any point. So if I move P over here, now this VQ is no longer perpendicular to PG, but all their properties remain true. So just this is sort of a thing they did back then where their conics were sort of more general than ours. You could put the vertex anywhere and all these properties would still hold, but just that the sort of like the axes are no longer perpendicular to each other. So these things will help you in understanding this proof. There are three properties of the ellipse that I'm going to show you just to get us started in the proof. And as we need the other ones, I'm going to introduce those. First property is still pretty widely known, and that's that if you have an ellipse and you have a point on the ellipse, if you connect that point to one focus and that point to the other focus and add those two distances, you'll get a constant. It's 6.8 here, and as I move this around, it continues to be 6.8. In Algebra 2, they also will show you that magic number is actually double, or it's equal to the major axis, this from A to C, 2 times AC. So that's one property Newton is going to use. The next property I'll show you, this one's not so widely known anymore, but if you have a point on an ellipse and you have this line tangent to the ellipse, and if you draw from that point to one focus and from that point to the other focus, that this angle, RPS, always equals this angle, ZPH. Sometimes that's called the reflective property of an ellipse. I've seen people talk about an elliptical pool table, that it would always, if you started at one focus, it would always bounce to the other. But that's the second property Newton's going to use. The third property is that if you if you take one of the foci of the ellipse and you draw this vertical line through, we're assuming here that this is what we could call now the major axis. We draw this line perpendicular to it, LM. That's called the latus rectum now, and that's obviously it's a constant. It stays constant for a particular ellipse, but that constant is actually equal to 2 times BC squared over AC. Notice how those are both 4.3, and I don't think that's a very widely known theorem nowadays, but that's the third theorem that he's going to use in this first part of his proof. Well, take a look at this pretty intimidating diagram we have here that Newton's going to use. I'm just going to spend the rest of this time just describing the properties of this diagram. So S and H are the foci of the ellipse. If you connect S and H, and you get the major axis, which goes to point A. P and Q are random points on the ellipse. You connect P to S. RPZ is tangent to the ellipse at that point. You make a line through Q tangent or parallel to RZ, and it's going to hit PS at point X. And you go PG, which is just starting at P, going through the center C. QX continues and hits that at V. DCK is the diameter that's parallel to RZ. It hits PS at point E. T is made so that QT is perpendicular to PS, and this point I is made so that if you start at H and make a line again parallel to RZ, it goes through PS at point I. And I've connected that as a dotted line. I've also connected P to H. There's going to be a couple of more auxiliary lines in this picture eventually, but this will get us through the first portion of Newton's proof. So that's going to be a good point to stop. So to be continued in part 6.